This video we are going to discuss about spherical polar coordinates and differential operators. So we discussed about our orthogonal curvilinear coordinates. We have studied about the differential operators, divergent, gradient, curl, Laplacian, etc. Here now we are going to derive for the spherical polar coordinates here. Okay, now we know what are spherical polar coordinates. We usually represent spherical polar coordinates by r theta phi. We have r is equal to xi plus yj plus zj. So r can be written as root of x square plus y square plus z square, which is a constant. That is, we were considering the concentric spheres about the origin. So r is the distance from the origin to the point P, which we have considered having the coordinates x, y and z. Okay, so here we are considering a coordinate that is x, y and z, and we considered a point P at a distance r from the center having the coordinates x, y and z. Okay, see here we have just drawn the planes parallel, and this is an xy plane. This is an xy plane, and we have drawn a plane that is parallel to z axis, then y axis and also x axis. If you are considering a point P here or reflection of P here, what will happen? There we don't have any z axis, so we have given the coordinates to be having a 0 value. So that means that this is lying in purely xy plane. Okay, now we know theta is the polar angle. If this is theta, what will be there? Then cos theta will be then what will be z? What will be the relation here? This will be this OZ, or this can be, if this is theta, this will be z cos theta. That means theta will be cos inverse r. Okay, now cos inverse z by r. Now if you are considering this xy plane, then what is the phi angle here? Phi angle opposite by adjacent tan phi will be y by x. Okay, y by x, or phi will be tan inverse y by x. Now we know what, now we want to know the relation between the Cartesian coordinates or rectangular coordinates and also our spherical coordinates. Okay, we are having the spherical coordinates r theta phi, and we are having our rectangular coordinates also x, y, z, etc. Now if this is O, as we told, and we are considered a point P at a distance, which is at a distance say R. Okay, now then if this is the OX, we have drawn the planes parallel as just before, as we have drawn the planes parallel here also. And then this will be, if this is theta, then this will be r sin theta. Then y will be represented by r sin theta sin phi. Z, as we already told, z cos theta, and this will be r sin theta cos phi. Okay, and we already know the relation x is equal to r sin theta cos phi, y is equal to r sin theta sin phi, and z is equal to r cos theta, where r is the value ranging from 0 to infinity, the polar angle ranges from 0 to pi, and the azimuthal or the longitudinal angle ranges from 0 to 2 pi. Now at present we are not concerned about the derivation of these relations. We are just straight away we are going to use this relation. Using this relation, let's first write a dx value, then we will write for dy and dz. See, dx can be written as dou by dou x of dx, dou by dou theta of dx, and dou x by dou phi of d phi. Now we are concerned only with the x here. So let us consider the x component, that is r sin theta cos phi. So first let us differentiate this with respect to r. When you differentiate with x with respect to r, we will get it as sin theta cos phi, right? Plus, now again we are differentiating x with respect to theta. When you are differentiating x with respect to theta, we will write r as such. Then for instead of sin theta, we can write it as cos theta cos phi. And now we are going to differentiate this with respect to phi. So again r sin theta, and cos phi is minus sin phi. Okay, this is dx. We have just taken now the x value only. We are going to differentiate x with respect to r theta and phi. Okay, now similarly if you want, we can write for dy also. So we will be getting as dy is equal to, so y we have considered r sin theta sin phi. So with respect, first differentiating with respect to r, we will get sin theta sin phi. Then we have differentiated with respect to theta, you will get instead of sin theta when you are differentiating cos theta. And then with respect to phi, when you are differentiating instead of sin theta, we have written as cos phi. Okay, cos sin phi we have written cos phi. Similarly, doing same thing with z. When you are differentiating with respect to r, we were getting cos theta dr, and when we are differentiating with respect to theta, cos theta is minus sin theta. So we got the three relations. Now we know what is in Cartesian coordinate, what is a ds or what is ds square is equal to dx square plus dy square plus dz square. Okay, now we are having the values of dx, dy and dz. Now we have to write the expression for line segment, line element. Line element in spherical polar coordinates. Let us write ds square is equal to, when you are going to write that, we can substitute for dx square, dy square and dz square. When we solve, on solving, we get ds square is equal to dr square plus r square d theta square plus r square sin square theta d phi square. See, solving it will take little bit time, so I have just written straight away the result. See, now we have already, when we were studying about our orthogonal curvilinear coordinates introduction, we had general equation as ds square is equal to h1 dq1 the whole square plus h2 dq2 the whole square plus h3 dq3 the whole square. See, this is the specific coordinate systems they are having. This is how we explained the specific coordinate systems having the scale factors h1, h2 and h3. Okay, and we were saying that in the ortholinear coordinates, curvilinear coordinates, hij is equal to 0, where I is not equal to j. See, now we are going to compare these two equations. We are going to compare these two equations, and comparing these two equations, we can write q1 is equal to r. See, dr square and dq square. So, this q1 is equal to r. q2 is equal to d theta or theta, and similarly q3 is equal to 5. And similarly, we are having the scaling factors h1 is equal to 1, h2 is equal to r, and h3 is equal to r sin theta. I hope this will be easier for you to remember. See, here h1 here corresponds to 1 only. Here there is no value, so we take it as 1 dr square. And here h2 square. See, here there is a square. So h2 square corresponds to r square. So we can say h2 equal to r. Similarly, here h3 square. h3 square, the coefficient of d phi square is r2 r square sin theta square. So when we were comparing the scaling factors as coefficients of dr square, d theta square and d phi square, we got h1 is equal to 1, h2, this is h2 is equal to r d theta, fine, I mean r, then h3 is equal to r sin theta. Similarly, we were comparing the coordinates, see, dq1 square and dr square. So r is equal to q1. dq2 square and d theta square. So q2 is equal to theta. And dq3 square is equal to d phi square. So q3 is equal to phi. So this is how we write the different, now this is how we get the scale, the value for scaling factors and the coordinates. Now we can write in terms of we can write the differential operators. What are our differential operators? Gradient, divergent, Laplacian and curl. So using this, let us take the formula and we can write the gradient, then we can write for divergence, Laplacian, etc. So let us let us start writing with our differential operators. Okay. Let us first start with our gradient or grad, which is represented by the symbol like this. See, in the curvilinear coordinates, we have already written that. We have written in curvilinear coordinates, grad psi is equal to, or we have written del psi is equal to, grad psi is equal to u1 by h1 dou psi by dou q1 plus u2 by h2 dou psi by dou q2 plus u3 by h3 dou psi by q3. This is our gradient psi, which we have already written. Okay, which we have in curvilinear coordinates. We have derived this and we got this. Now we are here. Now in the polar coordinates, what are the coordinates we are having? We are having u_r, u theta and u phi. Instead of u1, u2 and u3, we are having u_r, u theta and u phi. That is, u_r means along r, theta and along phi. Okay, r, theta and phi. Polar angle, azimuthal angle and the unit vector distance r. They are all unit vectors. Now, in spherical polar coordinates, we are having the values. What are the values we are having? See, we have already written, see, q1 is equal to r, q2 is equal to theta, q3 is equal to phi. Similarly, h1 is equal to 1, h2 is equal to r and h3 is equal to r sine theta. So, simply we are going to substitute it. See, let us see how we are going to substitute this one. Okay, when we are substituting these values here, I'll write the value, that is q1 is equal to r, q2 is equal to theta and q3 is equal to phi. h1 is equal to 1, h2 is equal to r and h3 is equal to r sine theta. We are going to substitute these values here in the above equation. When we are substituting, we have, instead of u1 we are having ur, instead of u2 you are having u theta and instead of u3 you are having u phi. So how can we substitute? Grad psi or del, whatever you want you can write. Grad psi is equal to, we will write a dou psi by, instead of q1 we are going to replace by r. So instead of q1 we can write it as r. And h1 is 1 here. Okay. And what is u1? u1 is r. So you can write it as ur by 1. Okay. Now, what is u2 here? u2 is u theta. What is h2? That is r. And what is q2? That is psi. So how can you write? You can write it as 1 by r. Okay. Dou psi by dou theta into u theta. Plus, what is u3? u3 means that is u phi. Okay. Now what is h3? h3 is r sine theta. So what is a dou psi by dou q3? So instead of q3 we are going to put it as phi. So what you can write? We can write it as dou by dou phi. Dou psi by dou phi. Okay. Or you can also write it as del, or gradient is simply equal to u of r into dou by dou r plus u of theta into 1 by r dou by dou theta. Here we are not using the function phi, we are just putting del only. Okay. Plus 1 by r sine theta dou by dou phi u of phi. Okay. This is the gradient value in the spherical polar coordinates. Now we want to do the divergence. Okay. Div v. Okay. See, we have the standard orthogonal curvilinear coordinates div v, which is represented as 1 by h1, h2, h3 dou by dou q1, v1, h2, h3 plus dou by dou q2. We can write it in a cyclic manner, simply like that. And instead of V2 here, we'll write it as V3, H3, H1. Okay. So just a cyclic manner, we have written only first term we need to study. So now we are having the divergence values again in the spherical polar coordinates. See first itself, see we outside we want H1 into H1, H2, H3. Okay, we want H1 product of H1, H2 and H3. What is the values for H1, H2 and H3? 1 into R sine theta. So we can write it as 1 by R square sine theta. Okay, now again instead of now see instead of Q1 we are having R here, then H2 and H1. H2 and H1 together we are having R. Okay, so how can we write instead of Q1 we are going to write it as R, and inside instead of V1 means V of R. V1 means V of R. Then what is H2 and H3? H2 and H3 is R and R sine theta, that is R square sine theta. Okay, now what is dq2? dq2 is d theta. Again V2 is V theta. What is H3 into H1? H1 is 1. That means R sine theta. Again what is Q3? Q3 is 5. V5 into H1 into H2. Okay. Or we can a little bit more if you can opening the bracket, and if you want we can write it as, finally we will get it as 1 by R square, that is we have taken or we have just opened the bracket and we have just rearranged and we got it as, see, 1 by R square dou by dou R square VR, plus again we have written as dou by dou theta of sin theta V theta. So when you are doing this inside the bracket, you will get a term extra which we have written here, and that is 1 by R sin theta. It is similar to that term, and again we have written this as 1 by R sin theta into dou V5 by dou R. So thing is we need to remember these things and just substitute. And next one is our, so we have studied the gradient and divergence. Now we need to know about the curl. In orthogonal curvilinear coordinates, curl V is written as 1 by H1, H2, H3. Our standard form is like this. Here also we need to just substitute only. Okay, now what we want to do, we are already having the values here, for we are going to just represent it. So what is H1, H2, H3? That is R square sin theta. Okay, what is H1? H1 is 1. And what is U1? U1 is our UR. U2 is our U theta. And U3 is our U5. Okay, now what is dou by dou Q1? Q1 is R. Q2 is theta and Q3 is 5. Now what is V1 into H1? H1 is 1 itself, and H2 is R. So we are writing it as R V theta, and H3 is R sin theta. So R sin theta into V5. So we have just substituted. Now we can open the bracket and we can write the term. So this will be UR into dou by dou theta R sin theta V5 minus dou by dou phi R V theta, again minus U5 U theta. So you can just simplify it. But this is the standard form and you can just simplify. Next is our one more thing, that is our Laplacian. Okay. So again in the orthogonal curvilinear coordinates, we have written Laplacian as del square psi is equal to again 1 by H1, H2, H3 into dou by dou Q1. See, just to see about only the first term, next terms will become as cyclic terms. This is our first term. See, second term, that is with respect to R we have Q1 we have written. Now with respect to Q2 we are going to write dou Q2. This see what will happen. See, H2 is remaining there itself, and again H2 will become H3 and H3 will become H1. H1 will become H2. Okay, then dou psi by, instead of dou Q, here it was Q1, sorry, and now it will become dou Q2. Now again this is dou by dou Q3. Okay, so what will happen? This H3 will become H1 and H1 will become H2 and H2 will become H3, dou psi by dou Q3. Okay, so this is what. Now again we are going to substitute with our standard values. So instead of Q1 we are having R, theta and phi, and H1 1 R and H3 is R sin theta. So when we are substituting, again we are getting R square sin theta, Q dou by dou Q1. What is dou by dou Q1 means? It is R. Now H2 and H3 is R and R sin theta, so it will become R square sin theta. H1 is 1, so denominator okay. Now dou psi by, as we told, Q1 is R plus Q2 is theta. Okay, H3 is R sin theta and H2 is R, so R and R will get cancelled and you will get it as only sin theta. Sin theta into dou psi by dou Q2. What is a dou Q2? Dou Q2 means, sorry, dou theta, right? Plus again dou by dou Q3. Q3 is dou phi. H1 is 1 and H2 is R, so it will be R. Okay, now H3 is divided by R sin theta, so what will happen? This R and R will get cancelled and you will be getting only 1 by sin theta into dou psi by dou Q3. Q3 is again 5. Okay, now if you want, again you can open the bracket as we have done for our divergence. As we have done for divergence, we can open the bracket and you can get the solution for Laplacian also. So the thing we have to remember is, we have to remember the values for Q1, Q2, Q3 and H1, H2, H3, and we are going to use the standard values in our curvilinear coordinates. Okay, so this is what we have discussed in spherical polar coordinates. Thank you.